The wave equation says wave speed is equal to the frequency times the wavelength. So doesn't it look like wave speed is directly proportional to frequency? And if you increase frequency, you increase speed? Seems reasonable, but let's watch and see. Here's a wave. I'm going to take the frequency and increase it, and I want you to watch to see, do those waves travel faster? What do you think? No, they're not catching up. The waves all travel at the same speed, regardless of the frequency. These waves don't get ahead. What we've just seen is that the speed of the wave is constant in any medium that you choose. Maybe the medium is water, like water waves, or a string, like we just saw, or perhaps you're using a slinky. The wave speed depends on just one thing. It depends on how quickly these particles can pull on each other. Because when this guy goes up, he pulls on his neighbor, which pulls on his neighbor. And if the force is transmitted quickly, the wave moves faster. The speed depends on how quickly the particles can transfer force to each other. So let's watch that. How do I let these particles transfer force more quickly? I increase the tension. I increase how much they're interacting. And look at how fast those waves go. If I suddenly increase the tension, those waves fly along. So wave speed, this is wrong. I need to erase this. This is wrong. Wave speed does not depend on frequency or wavelength. So what was my mistake earlier? When I went from the equation in blue to the proportionality in red, I made a crucial mistake. Can you see it? I assumed that lambda was a constant and I took it out. But that is not true. Lambda is not a constant. If you look at these three things, speed, frequency, and lambda, which one is constant? It's this. So if you want to write a proportionality, it's going to have to be 1 is proportional to frequency times lambda, or if we divide by lambda, we get this. Frequency and lambda wavelength are inversely proportional. Now, before we move on to the next thing, here's a challenge. Let's see if we can draw a wave that has twice the amplitude as the green and half the wavelength. Amplitude. What's amplitude? Oh yeah, amplitude is how high the wave is measured from the center line. So I need the new wave to go up twice as high, all the way to here, and not all the way down, but twice as low. And wavelength is how long the wave is. So you could measure it from crest to crest or trough to trough or any 2 points that are in phase. Instead of this wavelength, I need the wavelength to be half as big, just this size. So here's going to be one wave. The next there in blue is the next wave. Here's the next wave, and there's the last wave. All right, let's see if I can do this. I go twice as high, and it's half as long. Well, this is not great, but you get the idea. We're going to turn to the next page and solve 6 together. In 3.8 seconds, 2.5 cycles of a wave pass by a point. Well, this is how many pass. And this, is it period? Or is it some random interval of time? Well, it can't be period, because it's not how long it takes. It's not the time for one cycle to pass. We're choosing some random 2.5 cycles, So this has to be some random delta t. In the same time, the wave travels a distance of 1.9. Again, is this lambda or is it some random distance? It can't be wavelength because it's not the time or the distance for one cycle. So it's just some random distance. The amplitude of the wave is 0.62 meters. Calculate the frequency. Frequency is defined as the number of cycles that pass by a point per unit time. And so we can use this equation. We have 2.5 cycles in 3.8 seconds. And we can get our answer here. That's going to be 0.66 when we round for sig figs. 1 over a second is a hertz. Find the wave speed. We can't use this equation because we don't know speed, but we also don't know lambda. So we have to use instead, speed is distance over time. Now you can apply this equation, you can apply it to the particles. And how far do the particles travel? Well, if you watch one period, they go 1 amplitude, 2 amplitudes, 3 amplitudes, 4. The particles travel 4 amplitudes in one period. Or you can apply it to the speed of the wave itself. And we just plug in the wave's distance and how long it took. In this case, we're talking about the wave. We're going to get to particle speed down below in part E. So we're going to use this equation later, but right now we just have to plug in what was the distance the wave traveled. Whoops. The distance was 1.9 meters, and it took 3.8 seconds to go that distance. This is exactly 0.5. So I've given my answer 2 sig figs. Calculate the period. Well, period and frequency are inversely related. They're actually inverses of each other. It's not just a proportionality. They are exactly the inverse of each other. So I do 1 over my 0.66, except I'm going to use the unrounded value. And I get 1.52, which I'll round for sig figs to 1.5. To find the wavelength, now we can use this equation. We know speed and frequency. We seek wavelength. The speed again was 0.5. The frequency was that unrounded value, what was it? 657 ... times the lambda. And if you divide, you will get, let's see, 0.5 over 0.657. I should keep all the decimal places, but I think it rounds to 0.76. Calculate the average speed of the particles. This is where we use the particle speed equation. And you don't have the subscript p when you see the equation sheet, but if I were you, as soon as I saw this equation, I would add that subscript to remind myself this is only for particles. So the amplitude was 0.62, right? Yep. And the period again was the unrounded value, 1.52, right here. 4 times 0.62 over 1.52, 1.6. And look at this. The particles are moving much faster than the wave. The wave is only going 1/2 a meter per second, whereas on average, particles are going 3 times that roughly. So here's what's happening. You've got a slow wave where particles are, vibrating, oscillating up and forth really fast. See how fast that thing is going? By contrast, the crests themselves creep across pretty slowly.